data curves that we have. So you'll see functions that look like this. This is the general form for our logistic, the general form for our logistics. What is dp over dt? What does that dp dt represent? Generally speaking, what is p to the t? T is time, p is the
change in population.
Yeah, it's the change of population over time. What this says is 1 over p dp dt. So the change of population over time relates to the inverse of the actual population. It's relatively straightforward. And it's written like this in this nice form because if you're in this form, you get the key structures of the slope field. You get the key structures of the slope field. If you write it in this form, it's like standard equation of a circle or point slope form. If something's in point slope form, if something's in standard equation of a circle, you automatically have key information about the structure of what it looks like. So there's a bunch of calculus in here, but the idea is you're going to see slope fields that look like this. What's this L value going to represent? L value is going to be the Karen. Perfect. Very good harmony there. Both correct, both exactly what I was looking for. It's an asymptote and it is the carrying capacity. Absolutely. If you're above the carrying capacity, you generally come down towards it. If you're above, the population grows and then the growth slows. The rate of increase slows until it's really, really close. And then in real life situations, you already mentioned this, can you cross over asymptotes? Yeah. Well, in this type, absolutely. In real life situations, especially horizontal, can jump above, but then, whatever, the predator gets more prey and then it pushes it down, or there's not enough oxygen anymore for the bacteria to grow any further, so it pushes the population down. So there's some key points here. There's some very, very key points, and these can be absolutely asked about on the BC Calculus exam. They could give you a differential equation and then ask you, what's the carrying capacity? Where's the inflection point? Where is it concave up? Where is it concave down? These are the general pieces that you have to be able to identify. If you have L, the inflection point is always going to be an L over 2. It's going to be concave down above it. It's going to be concave up below it. And it's approximately exponential.
Everywhere it is, or just?
It's approximately exponential. Yeah, it is approximately exponential everywhere, yeah. It's just a reflection. The thing is, it's not generally perfect if we're modeling real data. So here are our three kind of general solution types, so to speak. If you're below L over 2, you're going to get a curve that looks like this. If you're between L over 2 and L, it's going to keep on increasing. And if you're above, it's going to decrease to it. Those are the general three paths. You're going to see this all the time in biology, if you haven't already. So, can someone just tell me what's going on right here? What work is being done here? You don't even have to look at the word, but we're starting with the general logistic, and what are they doing to it?
Separating variables.
They're separating variables and solving, right? They're separating. If this is the general, meaning, what's the only variable involved right here? There's lots of letters. What's the only variable? P is the only variable. K is a constant, and so is L. You're going to do this a lot in your life with mathematics, especially multivariable. I'm going to throw tons of letters at you, and just because something's a letter doesn't mean it's a variable. In this case, there's only one variable. What is it? P. So you have to separate. You use partial fractions. I like how they reference tables and things like that. But you use partial fractions. You keep on going. You keep on going. It's not something you have to do out. You can scan this to make sure it makes sense. Each piece, like, hey, look, we break something apart into a sum, and then we do the integral, and then we take care of signs, and then we take care of the constants. And what do you end up with? You end up with this right here. The solution to the logistic differential equation with the initial condition P naught t equals 0 is this right here. You'll see this. This you'll see all over the place, where A is equal to L minus the initial population over the initial population. This is a formula that you do need to memorize. You do need to memorize this. This will make your life much easier on any logistic question. Why?
Are you allowed to just write down the formula, you don't have to derive it or whatever?
Yes, absolutely. Yes. Or at least I'm 99% sure of that. Because here's the thing. This kind of separation of variables,
It's the same thing every time.
it's the same exact thing every single time. Exactly. It's the same thing every time. It's like, what's the derivative of sine? Cosine. Do you have to prove that every time you use it? No. This is a similar relationship. Here is the general, and then you need to know the solution. It's super important because you could absolutely get questions like this. Give the general solution to the logistic differential equation. How much time do you think gets wasted doing what on the AP exam sometimes? Like, this could be an absolute straightforward question on the AP exam, right? What's the wrong way to go about doing 1, 2, and 3? What's the wrong way? What should you not attempt to do?
Divide both sides by that. And then
Don't separate, don't try to do it, because you're going to do the same exact thing over and over again, and these numbers are just going to travel around, right? You need to remember what is the general form, and then what's the general solution. If you know the general form and the general solution, you can just plug in numbers. You can plug in numbers. So let's move that down there just so you can see first to translate that into the proper form. Factor out what?
P. 10 to 5 P.
Looks like it gets really, really weird.
Let's take out 10p or 5p. What do you want to take out?
Because then you have a 1.
10p? Because then you have 1 minus what? P over 2. Like that, right? So what's our k value? 10. What's our L value? 2. Can you memorize? Did you memorize the formula already? P of t is, it's L over what? Anybody remember? A e to the, is k 10 in this case, right? Negative, is that it right there? But what's L? 2? Is that correct? I think that's correct. But what does our A value equal? A is equal to what? Do you remember? L minus P naught over P naught. And does it tell us what P naught is right here? Yeah. It does. So we end up with A is equal to L minus, oh, what is L? It tells us, we know what L is. L is 2. So 2 minus what? L over 4 over L over 4, but what? Yeah, you said 0.5, right? So it's going to be L minus, it's going to be 1/2 over 1/2, like that. So that's going to be 3 over 2 all over 1/2. So what's that going to be? 3. So our final answer would be, so P of t in this case with this initial condition is 1 plus 3 e to the negative 10t. That is work, but is that a lot less? So 1 is equal to 3 e to the negative 10t. Is that correct?
Yeah.
Yay! So we do 1/3 is equal to e to the negative 10t. So log base what? Log base e of 1/3 is equal to what? E to the equal to what? Negative 10t. But 3 to, so that's log base, so that's ln of 3 to the what power? Ln of 3 to the negative 1 is equal to negative 10t. So that's negative ln 3 is equal to negative 10t. So 10t is equal to ln 3. So what does t equal? Ln 3 over 10. This answer key right here, so if you were to look this up, you see that right there? Look what they did.